So the question is, which is larger, e to the pi or pi to the e? Now, I think looking at these, it's not immediately clear which is going to be bigger. And in fact, you can calculate them and they're very, very close. Um, so there's not some easy approximation you can do with these two values. Um, so I think the way to start with this problem is to start by writing some kind of mathematical statement. And one way of doing this is we're going to assume, to start with, maybe we have a guess and we think that pi to the e is greater than e to the pi. Okay, and then we'll make some progress from this by applying some techniques, and then we'll either reach a result which is true or false. Then if it's true, then the argument will follow in reverse, and it will have shown our assumption to be right. Or if we reach a false conclusion, then we can conclude, like, by contradiction, the other way must have been true. Okay, so it's just easy to start with this to give us some structure, just to start the problem. So we'll call this star. Now, applying logarithms, which seems like the obvious thing to do, star is true if and only if, that's what this double implication arrow means, if and only if e log pi is greater than pi log e. This is to an arbitrary basis, arbitrary base of log. Call it k. So this is like log base k of pi. I'll write that. So like log base k of x. Okay, that's what we mean by log here, base k. And I think a reasonable thing to do from here is to collect like terms, right? If you're solving an equation with two variables, the normal technique is to collect like terms. The other thing is that this equality sign is preserved in this direction because log is an increasing function. Okay, that's kind of a subtle point, but that's why the inequality sign is preserved. For instance, some functions, when you apply them, will swap the inequality sign, but we're okay with log. So collecting like terms, this is true if and only if log pi over pi is greater than log e over e. Okay, and now the key thing to notice is the symmetry in this inequality. So in fact, these are both evaluations of the same function at different points. Specifically, the function f of x is log x over x. Okay? And so I guess our idea now is to get an idea of what this looks like, and from there that will help us decide which of these is bigger. Okay. So now we want to sketch the graph of log x over x. So maybe it will help by drawing a log x graph to start with. So log x looks something like this. Okay, this is y is log x, y x, and we could draw a graph of y as 1 over x, but I don't think we really need to. So a standard thing to start with in sketching a graph is, are there any stationary points? So we'll compute the derivative. So by the quotient rule, f prime of x is the derivative of log, which is 1 over x. We can choose base e here, so if you're happier with using base e, then that's fine, and maybe this is more familiar to you. So log base e of x, the derivative is 1 over x, multiplied by x, applying the quotient rule. Remember, f prime g minus f g prime over g squared is the quotient rule, minus log x, because the derivative of x is 1, divided by x squared. So f prime is 0, means that 1 minus log x is 0, which means that x equals k by adding log x to both sides and then raising both sides to the power k. Remember, k is the logarithm base. So in fact, here we can just call this e if we're going to use the natural logarithm. Yeah, okay. So I'll write this as e. That's the logarithm base. Okay. So there's a stationary point at x is e. Cool. What else do we know? Well, another good thing is to consider behavior for extreme values of x. So for this to be real, x has to be positive. So we'll only consider the positive quadrant. Log gets a bit messy for negative x. So I'll just write it again. F of x is log x over x. So the limit as x goes to infinity of f of x is equal to, well, as we go to infinity, log x goes to infinity and x goes to infinity. So this is going to be like a really big number over a really big number, and we're not really sure what happens there. So you can reason it two ways. Firstly, you could say, well, x increases much faster than log x, because d by dx of log x equals 1 over x. So this becomes almost flat as x becomes large, right? And so this is going to increase much slower than x, and so this is going to become 0. Alternatively, we can apply L'Hopital's. Okay, so that says that so I'll write a statement of L'Hopital's briefly. The limit of f of x over g of x as x approaches some value a is equal to the limit of f prime of x over g prime of x as x approaches a, where f over g at value to a is indeterminate. Okay, I've discussed with I think I've discussed with all the people this is relevant to, the conditions, and so hopefully you have it written down on the paper from our mock interviews. But just so you remember, this is the idea. So this is the limit of the derivative of log, which is 1 over x, divided by the derivative of x, which is 1. And as x approaches infinity, here, this is clearly 0, okay? Agreeing with our logic that x increases much faster than log x does, okay? So we know that for large values of x, f of x is going to be 0, okay? So I'll start circling some of the key facts. So this is our stationary point that we calculated, and the limit as x gets large is 0. And now we need to look at behavior near the origin, right? That's the other extreme value that we're interested in. So the limit as x approaches 0 of f of x is equal to, well, let's think about this. So as x goes towards 0, it's going to be 0. As log x goes towards 0, this is going to be negative infinity. Okay, so it's going to be like negative infinity divided by something really small and positive. So if you divide by a small number, that makes your number really big. So we have a big number divided by a small number, that means it's going to be really big, and we have a minus over a plus. So it's going to be minus a really big number. Okay, so this is going to be negative infinity, and we'll put a box around this. And so from that, we can sketch our graph. Okay, so I'll rewrite it. So we're sketching f of x is log x over x. Remember, just to recap, the whole point of this is to determine which of these is bigger. That's why we're going off on this tangent, okay? It's completely relevant. Because if we see where these points lie, i.e. where x is pi and where x is e for our function f, then this is going to determine which of these is bigger just by looking at the graph line, okay? So, so f of x is this, and we have, again, let's look at what we did before. So we know there's one stationary point at x is e. As x goes to infinity, it goes to 0. And as x goes to 0, we go to negative infinity. So let's see if we can draw that. Okay, so x close to 0, we're going from negative infinity. We have a stationary point at e, which we know must be a maximum because as x goes to infinity, we're going to 0. Okay, so this is a e, so our x-axis. This is our y-axis. Like y equal to f of x here is what we're plotting. And so this is f of e, which is log e over e. Well, this looks kind of familiar because this is what came up here. And so the other value we're interested in is where x is about pi. So let's say pi is about there. So this value here is log pi over pi. But the important thing is this log e over e, i.e. f evaluated at e, is a maximum. So all of the values must be smaller than it, okay? And so in particular, so therefore, log pi over pi is less than log e over e. And remember, so here, by assuming this, we reach this result. This is true exactly when this is true. But this is wrong. This statement that we derived from our assumption is false. So this means contradiction. And so, yeah, I can write here. Contradiction implies our assumption must have been false, i.e. We assumed that pi to the e is greater than e to the pi. So pi to the e is not greater than e to the pi. So e to the pi is greater than pi to the e. And we're done.